Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers.
Ladies and gentlemen, welcome back to the Ephemeris podcast. I'm your host, Aphelion. Thank you for joining me for another episode in Chapter 2, Season 3 of the podcast, where we're looking at recent stories in the world of astronomy. And just like usual, we're going to have three stories for this week, or actually, technically, last week we only had two, but this week we're going to have three like usual. The first story is going to be about Asteroid Bennu and what we discovered about the asteroid itself. Then we're going to get into stellar streams in the Milky Way's halo. And then lastly, we will talk about the connection between supermassive black holes and dark matter. So without further ado, let's go ahead and get into these stories. So first, we're going to freshen things up, look at asteroids a little bit today, because we're usually about stuff that's not in our solar system, but today we're going to look at things that might exist in our solar system. Or, well, asteroids do exist in our solar system. And one of them is Bennu. So, Bennu is a carbonaceous asteroid. That is its classification, and it's also known as a C-type asteroid. Carbonaceous asteroids are actually the most common type of asteroids. There's the C-type, then there's metallic, which is the M-type, and then there's silicaceous, which is the S-type. And those three constitute all of the asteroids, but the most common type is carbonaceous, C-type. And as the name would suggest, their primary ingredient is carbon. C-type asteroids also have very low albedos, and albedo being the amount of sunlight that an asteroid reflects. So essentially, these asteroids are quite dark. Bennu specifically has a spheroidal shape, which makes it look like a spinning top, and it rotates retrograde to its orbit. So some really quick fun facts for you there. It's also a bit unusual that Bennu is a near-Earth asteroid. When C-type asteroids are typically a bit further away. I believe it's something like 3 astronomical units from the sun where you usually find them. But in terms of what new information we've gotten from Bennu in recent times, we did collect its geographic information through OSIRIS-REx. Hopefully I'm saying that correctly. And that was in 2018, 2 years after its launch. And then Bennu's surface, we actually reached it with OSIRIS-REx in 2020. We collected samples, and the samples made it back to us in 2023. And May of 2024 is when they did a detailed report on the analysis that was done with the samples. A little bit late to the story, therefore, but it's fine because, generally I think a range of a couple months is not too bad. I keep my collections of articles with me for quite a bit, so some of these stories do happen to be a little bit old. But anyways, what did we find on Asteroid Bennu that was so special? That is the question here. And according to several articles, Bennu's dust was rich in carbon, but also nitrogen, sodium magnesium phosphate, carbonates, and other compounds that are precursors to biological building blocks like amino acids and sugars. Clays like serpentine, smectite, and magnetite were also found, which on Earth is usually found in ridges that are in the middle of the ocean. Lastly, researchers found evidence of fluid flow through fractures that were in this complex sheet of minerals. I think the technical name for it is phyllosilicates, but I couldn't really break down the definition of a phyllosilicate, so we're just going to call it complex sheets of minerals. So yeah, they found fluid flow in these sheets through the fractures that they saw when they collected the samples. And most of this has to do with possible hydrothermal processes, so not going to get into much detail there. And lastly, they found some of the particles have hummocky shapes resembling cauliflower, which on Earth is you'd typically find it in regions that are exposed to shallow seas. So a lot of evidence here that might suggest that there was water on Bennu's surface and that there could have been life. So, also, since Bennu's minerals can be traced back close to the formation of the solar system, these findings are especially helpful. And, the fact that Bennu is a near-Earth asteroid, it very well could have had an influence on life on Earth itself, because we have discovered in the past that a lot of necessary ingredients for life were delivered through asteroids. Perhaps not from Bennu because it kind of had it on its own, but, possible. And it's definitely a subject that is worth exploring even more. But, yeah, some really, really cool findings here on Bennu's surface. And that's where I'm going to wrap up the article right there. So our second story, swiftly moving on, is about stellar streams near the center of the Milky Way galaxy. However, a point to make about these two streams we will investigate is their age, because we have looked at, like satellite galaxies-ish in, the Milky Way, or, some like stuff that surrounds the Andromeda, but here we're talking about old stellar streams, ancient stellar streams. And their age is estimated to be at least 12 billion years old, which means they formed before the Milky Way was actually the Milky Way. It was at a time when the Milky Way was in the process of formation. So that's pretty serious business, because then we have a lot to unpack with where did these stars come from. Apparently detecting these stars in and of itself is quite surprising just because of their age, but no further explanation was given on that, so we're just going to leave that fact right there. What we do have is the details about the efforts that went into finding these stars itself. So the researchers behind this whole project, they were previous students of a class ran by Anna Frabel at MIT about analyzing ancient stars and their origins. According to articles that I referenced, quote, they were looking for stars with measurements of starlight or spectra that indicated low abundances of strontium and barium. The low chemical abundance was a solid hint that the three stars originally formed about 12 to 13 billion years ago, and the three stars that are mentioned here are the ones that were the initial stars that were found in the stellar stream. So yeah, the team would then go on to, keep looking at stars that belong to this small accelerated stellar stream, as it's called. It's also abbreviated as SAS. So yeah, what then came out of this, right? Because obviously these observations can't be made on a whim at any time. But what's the point, right? Did we actually end up finding the origin of the stars, as the researchers were meant to do? So the prediction of sort of these SASs, or small accelerated stellar systems, is that they're remnants of galaxies that merged with the Milky Way when, the universe was quite young, and, it was during the early universe. Such a theory would easily explain the low abundances of more complex chemicals, and it would contribute to the possibility that the Milky Way was a part of many collisions in its early life. There are some other contrary theories to all of these observations that we've talked about with these unusual stars. One contrary theory is that it is possible that the newfound stars were born in situ and merely swept from deep within our galaxy to their discovery location about 26,000 light years from the center. The reason why this theory is, has any basis really, is because there are still some elements in these stellar streams that are usually found in Milky Way stars. They weren't specifically named, the elements in the article, so I can't provide further detail. You're welcome to just take that fact with a grain of salt. But another, reason that might contribute to the basis of this argument is the bars of the Milky Way could have pushed out a pile of stars, which would be analogous to a fan pushing air molecules, out of its vicinity to create airflow. So The latter theory, with all of that, has been subject to slightly more scrutiny than the former. So, the preferred theory is definitely that these stars were never actually a part of like the Milky Way. It was more of they formed in a different galaxy that merged in the Milky Way. Yeah. So that is what we know about the two ancient stellar streams that are near the center of our Milky Way galaxy. And so we will swiftly move on again to the third story of the episode, where we're going to talk about black hole mergers and what's so complicated about them and whether there's actually a solution to these complications. So in astrophysics, we have a problem when it comes to black hole dynamics. We don't have an explanation for the merging of black holes as they close within a couple parsecs of each other. So like a parsec, I believe, is like 3.26 light years. So yeah, a couple light years between the black holes is when there's problems. And as we've discussed before, gravitational collisions are never head on in the way we would imagine like a regular 2D collision. Like that's sort of not how they work. And the last time we talked about that was like sort of the collision with galaxies. The same follows for black holes. But when we look at black holes specifically, there are effects that would make it impossible for them to merge, like theoretically. One effect is gravitational drag, and that's really the main effect. It's also called dynamical friction, but I like to include the gravitational part to it. When a black hole interacts with any object, it accelerates the object at the cost of its own kinetic energy and momentum. So that's the baseline definition. So if a star comes close to a black hole without falling into it, the black hole loses momentum and kinetic energy, accelerating the star. Now, to make this a little bit more intuitive to think about, I'm going to break the rule of seeing gravitational interactions as head-on for just a second. Like if you can imagine, you put a fidget spinner on a table, and you put a ball between the fidget spinner, and you spin the fidget spinner towards the ball, and then it creates like a classic 2D collision that like flings the ball in a straight path away from the spinner, in any given direction. That collision specifically would increase the momentum and energy of the ball at the cost of the fidget spinner, right? That would be a classic mechanic, phenomena that is quite familiar if you do end up sort of studying that, right? This situation is like kind of analogous to what you might see between a black hole and a star, but when you flip it back to a black hole and a star, the black hole isn't just an object that's given momentum and energy anymore. I would prefer like looking at it as a deep gravitational energy well. So when a star comes by, the black hole is attempting to get this star to add to the well because it's got a bunch of gravitational energy, right? And it exerts a force over a distance that attempts to lower the energy level of the star and sort of bring it towards the black hole. But if the star doesn't get sucked into the well, we can't forget that gravity as a force is a mutual attraction, like equal and opposite kind of thing. So in the process of trying to gravitationally influence the star is doing the same to the black hole, and so you could have pretty much the exact same thing that the star is doing, or the same exact thing that the black hole is doing with what the star is doing to the black hole. So let me just put that in other words because I made it a little bit more complicated than I needed to. So if the black hole doesn't make the star a part of the well or bring it closer to it and sort of bring it in, then the star kind of takes from the well, if that makes sense. I will happily admit that this is not an objectively correct way to explain the effect. I'm sure there's better explanations out there, but to me it helps. Like this explanation specifically helps me intuitively think about it. So hopefully it will help you as well. So anyways, whatever you imagine this effect to be, when it exists between two black holes, as I would say, two deep gravitational wells, you can expect that it's not so simple since both objects within the interaction are equivalent. So it'll become kind of like a 1v1 tug of war, where the amount that the rope moves increases to the point that the person who comes away with the rope just like launches away from the other person. That's how I like to think about what would happen if you were to, theoretically simulate a black hole merger with the gravitational drag effect. So, is there a solution to this problem? Apparently, a gravitational wave hum has been found in the background of the universe that may be attributable to dark matter. So let's just talk about this gravitational hum for a really brief moment here. I brought in a quote from a separate article that states, quote, "Several teams around the world have independently found a signal in the timing of flashing stars called pulsars that points to giant long wavelength gravitational waves rolling through the galaxy. It's not quite a detection of those gravitational waves yet, but there is more than a 99% chance that what we're looking at is something significant." So in this specific case study, what we found is the regularity of sort of pulsars indicated that there was a bit of a background hum in terms of gravitational waves, and occasionally you get the actual gravitational waves. So anyways, the idea that we can just simply link the gravitational wave hum that we've discovered previously with dark matter, it's a long shot, primarily because we barely even know what dark matter is, and we've struggled to figure out a way to detect it. But just bear with me here, because there are some details in the article that I looked at specifically for this story that I think bring up some good points in why we should reconsider the possibility of dark matter actually having an important role in black hole mergers. So the first explanation that was given by this article here states, quote, "Alonso Alvarez and his colleagues," so the people who worked on the research, "wondered if we were being too hasty throwing out dark matter as a solution. So they designed mathematical models to test it. And they found that dark matter that interacts with itself can stay in the vicinity of merging supermassive black holes, giving the black holes something to pass their last orbital energy onto so they can finally embrace, forming one extra large supermassive black hole." Okay, so even though exactly how this works is not quite clear, there are still some mention of at least redeemable qualities that might actually create a bit of a link. So let's keep going. At the moment, the results are fairly theoretical, but they make predictions that can be observed. For example, the findings predict a softening of the gravitational wave background hum, of which hints have already been seen, as we talked about very briefly. And the results can also be used to understand the halos of dark matter that surround galaxies throughout the universe, since the particles must interact on a galactic scale to be able to resolve the final parsec problem. Okay, so now what this quote is telling us is that if we're going to reconsider it, right, that the physics would check out theoretically, then there's actually maybe some ways we can detect it for real, right? Looking at galaxies and sort of the distribution of dark matter within them. There's a whole lot of stories about that, like low surface brightness galaxies and all that. So hopefully you see now that given time, there might be some merit to actually attributing dark matter to what's going on here, even though the details still aren't quite clear. I know dark matter and dark energy is all the hype with almost all the research that's done these days, but I just wanted to entertain it for a quick second for one article, because I think this idea of the final parsec problem is actually quite interesting, and no matter what solutions are proposed, they're going to be quite significant. So yeah, that is all I have for this episode today. Hopefully you all enjoyed listening to the stories in this episode. If you are new to this podcast and you enjoyed the content, considering watching more of my content, and if you continue to like it, consider subscribing. If you're on Spotify, same goes as well. And yeah, I have some cool episodes planned in the future, and we might see a little bit of a shift in the format since it has been quite a few episodes within season 3 here. But other than that, I will see you all next week. Peace.